morning, students. This is Dr.GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. In previous session, we have learned the design of a planes coupling procedure. So, in this session, we will see the problems on planes coupling, how to solve planes coupling problem. So, take this example. Design and draw a protective type of cast iron planes coupling for a steel shaft transmitting 15 kilowatts at 200 rpm. The given type of coupling is protective type of cast iron planes coupling. So already we have studied the planes couplings are three types. One is unprotected and protected type. Another one is marine type of planes coupling. So here the protective and unprotected both are same. So only difference is having some protection cover the protective type of cast iron planes coupling. So in this example, design and draw. First you design a protective type planes coupling with all dimensions, and then draw a protective type of cast iron planes coupling. So according to the calculated dimensions, you should draw protective type of cast iron planes coupling. So given material is here steel shaft for a steel shaft transmitting power 15 kilowatts at 200 rpm. The speed is 200 rpm and the given power is 15 kilowatts. Having an allowable shear stress is 40 megapascal. The working stress in the bolt should not exceed 30 megapascal. So the given allowable shear stress is 40 and the working stress in the bolt should not exceed 30 for bolts, and assume that the same material is used for shaft and key, and that crushing stress is twice the value of its shear stress. Here crushing stress is 2 times of values of the shear stress. The crushing stress is 2 times of the shear stress. Assume the same material used for a shaft. The shaft material is steel. Here also key, same material. The maximum torque is here given condition 25% greater than the full load torque. Here 25% greater than the full load torque. So 25% greater. So 100 plus 25, 125%. So that is 1.25. The shear stress for cast iron is 14 megapascal. The cast iron material is 14 megapascal. The plane material is cast iron planes. So that's why here you should take the shear stress for cast iron is 14 megapascal. The plane material cast iron and shaft material is mild steel, and key material also steel, and bolt material here. So assume same material, the material for a shaft. Here solution given. First of all, given data. What are the data available? The given data. Separately for shaft data and bolt data and key data. Shown here, the shaft data, the power transmitting 15 kilowatts, you can convert into watts, and speed 200 rpm, and shear stress 40 megapascal. So convert into mm square, 40 Newton per mm square. And tau maximum is 1.25 times of T mean, 25% greater than the torque. So the crushing shear strength 40 megapascal, the shear stress for planes. So for bolt material, given shear stress is 30 megapascal, and here given condition is the crushing stress for key material is 2 times of the shear stress of key material. So the protective type of cast iron planes coupling is designed as discussed in the next coming slides. See the diagram shown. Design for hub, first step, design for key, design for planes, and design for bolts. Here shown in this shaft 1 and another end, and planes 1 and planes 2, and bolt and nut, and keyway, key, hub, so first hub dimensions you should calculate, and then the key dimensions and flange dimensions and bolt. First step is design for hub. So as we discussed in earlier session, for hub we know that the outer diameter of the hub is usually taken as twice the diameter of the shaft. So capital D is equal to 2 times of the D. So the length of the hub is taken as 1.5 times of the D. First thing we need is the diameter of the shaft. First step is diameter of the shaft. If you know the diameter of the shaft, you can calculate remaining dimensions. How do you calculate diameter of the shaft? By using torsion equation. T max is equal to pi by 16 into tau into dq. So calculate D. So you will get torsion is 895 into 10 cube Newton mm, and you can calculate diameter of the shaft is 48.4. You can say 50 mm according to standard values. This is diameter of the shaft. Next, the outer diameter of the hub you can calculate. D is equal to 2 times of the D, 2 times of shaft diameter. So 2 times of 50, so 100 mm. The length of the hub 1.5 times of the shaft diameter. Your given condition is here T max is equal to 1.52 times of T mean. So T mean is equal to 60 P by 2 pi n. So P already you know the power, and n also you know. Putting value in above equation, you will get the T mean. So T max. T mean value 716. So this value substitute in above equation. In this equation, you will get T max. The required dimensions will be the required dimensions of hub, capital D, the outer diameter. Already we have calculated 100 mm. So length 1.5 times of D. Now we check the induced shear stress for the hub material. So hub material is cast iron. Considering the hub as a hollow shaft. So hollow shaft the area is 5 by 4 into the area is already you know the 5 by 4 into d to the power 4 minus d to the power 4 by capital small d to the power 4 by capital D. By using the empirical relation of hollow shaft, you can calculate the maximum torque transmitted 5 by 16 into tau into capital D to the power 4 minus small d to the power 4 by capital. For simplicity, you can take here K as di by d naught. So di is internal diameter of the shaft and outer diameter of the shaft, as we learned in the shaft design. So substitute those values, you will get maximum torque transmitted. Since the induced shear stress in the hub is less than the permissible value of 14 megapascal, here the calculated induced shear stress is 4.86 megapascal. For given condition, the shear stress for flange, for cast iron flange material, 14 megapascal. So this value is less than the given value, permissible value, then our design is safe. So always you should check for this shear stress or crushing stress for safe design. Next, second step, design for key. What are the dimensions of the key? Since the crushing stress for the key material is twice its shear stress, the given condition. So here the square key may be used. You can find from standard table the 50 diameter shaft. For a 50 diameter shaft, what are the dimensions of the key? Square key, width and thickness are same. You can find the length of the key equal to the length of the hub. Length of the hub is equal to 1.5 times of shaft diameter. Now let us now check the induced shear stress in the key by considering it is shearing and crushing. Considering the key in shearing, considering key in crushing. Check for shearing strength, check for crushing strength. We know that the maximum torque transmitted T is equal to L into width of the key into shear stress of the key into the radius d by 2. Radius of the shaft. So by using this empirical relation, you can calculate the crushing shear strength in the key. What is the shear stress induced? Key is 29.8 megapascal. To similarly calculate crushing strength. So I know that the maximum torque transmitted L into T by 2. Here L into T by 2 is the crushing area. The crushing area of the key. Here shearing area. So this is the difference between this shearing and crushing. When considering the key in shearing, when considering the key in crushing. L into T by 2. So calculate your crushing strength. You will get 59.6 megapascal. Since the induced shear and crushing stresses in the key are less than the permissible stresses, or already given in our problem, the shear stress and the crushing stress. How much given? Shear stress and crushing stress 30 and the crushing stress is 60, 2 times of the crushing. So this one is less than the 30 and this one less than the 60. So that the above design for key is safe. Next, third one, design for flange. The thickness of the flange is taken as 0.5 times of D. And calculate torque transmitted. Circumference of the hub into thickness of the flange, multiply with the shear stress of flange and the radius of. Already you know this equation. Now check the induced shear stress in the flange. By considering the flange at the junction of the hub in shear, we know that the maximum torque transmitted T is equal to pi into 100 square by 2 into tau c into 25. So D is equal to 100 here. So here you can calculate shear stress 2.5 megapascal. So that the induced shear stress in the flange is less than the permissible value. The shear stress given for flange material is 14 megapascal. Therefore, the above design is safe. The above design means whatever you calculated the dimensions of the plates are in a safe condition. See, in here given one table, shaft diameter and a number of bolts. According to the shaft diameter, you can choose number of bolts. If your diameter of the shaft is 35 to 55 range, then you can take number of bolts 4. Similarly, 56 to 156 and 151 to 238, 231 to 390, 10, and above 390, 12. Here, diameter of the shaft, how much? Calculate diameter of the shaft is here. Diameter of the shaft is 50. So, 35 to 50, you can choose here number of bolts are 4. Next, design for bolts is shown tabular form. Shaft diameter and a cross section. If the shaft diameter is 50, you can take the width and thickness of key, and the shaft diameter up to including and cross section. So if the shaft diameter is more, you can take these values. So here the key dimensions are 16 mm width and 10 mm thickness. Clear? So like this, how to solve the problem of a flanged coupling. So these are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.